From heating our homes to powering transport, alkanes provide us with the energy we use every day. But does it actually matter how they burn? In this video, we'll explore what determines whether combustion is complete or incomplete, how to write the equations for both, and why the conditions in which a fuel burns make such a big difference. So grab your Learn Pack and let's get started. Many of the short-chain alkanes we use every day are actually used as fuels. Natural gas heats our homes, petrol and diesel power our cars, and kerosene is used as jet fuel. But what do we actually mean when we say something is a fuel? Well, a fuel is a substance that releases energy when it is burnt. When a fuel undergoes combustion, it reacts with oxygen in the air. This reaction releases energy, usually as heat energy, which we can then use. For example, when we burn natural gas in a boiler, the energy released by the combustion reaction is transferred to the water, allowing us to heat our homes. When we burn petrol in an engine, the energy released is used to produce movement. Alkanes are particularly useful as fuels because they release large quantities of energy per gram of fuel burned. However, not all alkanes make equally useful fuels. Short-chain alkanes are generally preferred because they are more volatile, which means they evaporate more readily, allowing them to mix with oxygen and ignite more easily. But regardless of which alkane we burn, the chemistry is based on the same principle. Carbon and hydrogen atoms in the alkane react with oxygen during a combustion reaction to release energy and form new products. So if we completely combust an alkane, we should expect the products to be carbon dioxide and water. But what conditions are needed for combustion to be complete? We've already said that combustion is the reaction of a fuel with oxygen, but for combustion to be complete, there must be a plentiful supply of oxygen. In other words, there needs to be enough oxygen available for every carbon atom and every hydrogen atom in the alkane to be fully oxidized. To see this in action, let's start with the simplest alkane, methane. Methane has the molecular formula CH4. If methane combusts completely, what product should we expect? Well, methane, like all alkanes, only contains carbon and hydrogen atoms. When burnt in a plentiful supply of oxygen, the carbon atoms will form carbon dioxide and the hydrogen atoms will form water. So we've got methane reacting with oxygen to form carbon dioxide and water. But now we need to balance the equation. And this raises an important point in A-level chemistry. You must always write balanced equations. The exam question won't necessarily tell you to balance it, but the examiners are always expecting you to give balanced equations. Now, rather than trying to balance everything at once, I always recommend following the exact same order each and every time. First, balance the carbon atoms. Now, this is actually quite easy. However many carbon atoms there are represented in the hydrocarbon is exactly the number of carbon dioxide molecules formed during complete combustion. Here we have one carbon atom in our molecule of methane, and so we will only make one molecule of carbon dioxide. As we don't write ones in chemical equations, I can just leave things as they are. Next, balance the hydrogen atoms. Now this is a little bit trickier, but again there's a method we can use every single time. However many hydrogen atoms there are represented in the hydrocarbon, you form half that number of water molecules. And that's because each water molecule contains 2 hydrogen atoms. So if you have 10 hydrogen atoms in your alkane, you would form 5 water molecules as half of 10 is 5. However, methane only contains 4 hydrogen atoms, and so we will make 2 molecules of water. Once you've balanced the hydrogen atoms, last but not least, we need to balance the oxygen atoms. To do this, first count the number of oxygen atoms you have in total on the right-hand side of your equation. This is the total you now need to make sure you have on the left. If your fuel already contains oxygen atoms, they're going to count towards that total. So subtract them before deciding how many oxygen molecules are needed. And then, because each oxygen molecule contains 2 oxygen atoms, divide your answer by 2. And the great news is that at A-level chemistry, you're allowed to use halves when balancing equations, so you no longer need to worry about multiplying everything up just to get whole numbers. So looking at our equation for the complete combustion of methane, on the right we have 2 oxygen atoms in carbon dioxide, plus another 2 oxygen atoms from the water molecules, making 4 oxygen atoms altogether on the right-hand side. Our fuel doesn't contain any oxygen atoms, so half of 4 gives us 2, We therefore need 2 molecules of oxygen on the left-hand side to balance our equation, giving us CH4 plus 2O2 goes to CO2 plus 2H2O. And that's exactly the same method you can use every time you're writing an equation for combustion reactions. Let's have a look at another one to prove it. This time we'll burn propane. And we'll start exactly as before. Propane has a molecular formula C3H8, and so there are 3 carbon atoms. We therefore need 3 carbon dioxide molecules. Propane contains 8 hydrogen atoms, half of 8 is 4, so we need 4 water molecules. Finally, count the oxygen atoms on the right-hand side. The 3 carbon dioxide molecules contain 6 oxygen atoms, and the 4 water molecules give us an additional 4 oxygen atoms, making a total of 10. There's no oxygen atoms in our fuel, and so we can halve 10 to give us 5, so we need 5 molecules of oxygen. This then gives us C3H8 plus 5O2 goes to 3CO2 plus 4H2O as our overall balanced equation. So it's all about developing a pattern or a routine, and developing consistent patterns or routines is crucial when studying A-level chemistry, as it saves you having to work from scratch every single time. Instead, you can just think, oh, it's a complete combustion equation. Right, this is what I do. Balance the carbons. The number of carbons on the left equals the number of CO2 molecules on the right. Balance the hydrogens. The number of hydrogens on the left halved equals the number of water molecules. Then finally, balance the oxygens. Count the number of oxygen atoms in total on the right, subtract the number of oxygen atoms in the fuel if there are any, and divide that number by 2, and that's how many oxygen molecules you need on the left. And then finally, I'd just recommend giving it a quick once-over to make sure you haven't made any silly mistakes. And once you're comfortable with that routine, you can balance the complete combustion of almost any organic compound. For example, an exam question might ask you to write the equation for the complete combustion of an ester. Students often panic because the molecule looks much more complicated, but the process is exactly the same. The only thing you need to remember is that the ester already contains some oxygen atoms, so when you're counting oxygen atoms at the end, don't forget to subtract the oxygen that's already present in the fuel. The method hasn't changed, that final step just requires attention to detail. So complete combustion is actually quite straightforward. However, fuels don't always burn under ideal conditions. When fuels burn with an insufficient supply of oxygen, incomplete combustion occurs. During incomplete combustion, the hydrogen atoms in the fuel still form water, but the carbon atoms are no longer completely oxidized to carbon dioxide. Instead, the carbon atoms may form carbon monoxide, solid carbon, or a mixture of the two. This happens because there isn't enough oxygen available to completely oxidize every carbon atom in the fuel. In a car engine, for example, the fuel and oxygen aren't always perfectly mixed, so there may not always be enough oxygen available for complete combustion to occur. So depending upon the amount of oxygen available, the products of combustion can change. In a plentiful supply of oxygen, complete combustion occurs and we get carbon dioxide and water as our products. However, as the supply of oxygen decreases, the carbon atoms become less oxidized. We might get carbon monoxide and water. Or if there's slightly less oxygen available, we get carbon or soot, carbon monoxide and water. And in a very limited supply, we might just get carbon and water being formed as our products. Now, it's important to recognize that the method for writing equations for these reactions is still exactly the same as before. We still need to balance the carbon atoms, we still need to balance the hydrogen atoms, and we still need to balance the oxygen atoms. The only thing that changes is where the carbon atoms end up. Instead of every carbon atom ending up in carbon dioxide, some carbon atoms form carbon monoxide, or in some cases, solid carbon. Let's take a look at a couple of examples. We'll start with the incomplete combustion of propane that forms carbon monoxide and water. Propane has 3 carbon atoms, so we would have 3 molecules of carbon monoxide. It has 8 hydrogen atoms, and so there would be 4 molecules of water. Add up the oxygens on the right, and we get 3 from the carbon monoxide and 4 from the water, giving us a total of 7. There are no oxygens in our fuel, so we don't need to take anything away, and then we can divide by 2 to give us 3.5 molecules of oxygen on the left. But what if we get a mixture of carbon monoxide and carbon? Well, I could split the carbons any way I like. I'm going to go with 2 carbon monoxide and just the 1 carbon. We still have 8 hydrogens on the left, which is going to give us 4 waters on the right. Now, just as before, add up the oxygens on the right. 2 from the carbon monoxides and 4 from the waters gives me 6. There's no oxygen in the fuel itself, and so I need 3 molecules of oxygen on the left. Now let's stick with propane, but think about just producing carbon. 3 carbons on the left, so 3 carbons on the right. 8 hydrogens on the left, so 4 molecules of water. 4 oxygens on the right, none in the fuel means 2 molecules of oxygen on the left. All very simple. And that's the great thing about the method we looked at previously. It works for both complete and incomplete combustion reactions. We just need to get into the habit of following it every single time. The only difference is that the limited supply of oxygen means that the carbon atoms in our fuel cannot all be fully oxidized, and that has an important consequence. Complete combustion releases the maximum possible amount of energy from a fuel because the fuel is completely oxidized. During incomplete combustion, however, less energy is released because the oxidation is incomplete. This results in less energy being released per gram of fuel, so more fuel is needed to produce the same amount of useful energy. But reduced efficiency isn't our only problem. Carbon monoxide also poses a significant danger. Carbon monoxide is a colourless and odourless gas, which makes it particularly dangerous because it can be difficult to detect. However, the main reason carbon monoxide is harmful is because it is poisonous. When we breathe in carbon monoxide, it enters our bloodstream and binds to hemoglobin in our red blood cells. Normally, hemoglobin carries oxygen around the body. However, carbon monoxide binds much more strongly to hemoglobin than oxygen does, preventing hemoglobin from carrying oxygen effectively. This means less oxygen can be transported around the body, which can lead to serious health problems and at high enough concentrations can even be fatal. This is why incomplete combustion is particularly dangerous in enclosed spaces, where carbon monoxide can build up to harmful concentrations. For example, if a central heating boiler isn't regularly maintained, incomplete combustion can occur, producing carbon monoxide instead of carbon dioxide, putting the lives of those living in the house at risk. This is why modern boilers are designed to help ensure complete combustion occurs, both to maximize energy efficiency, but also to prevent the formation of toxic carbon monoxide. So although incomplete combustion can still release energy from a fuel, it is far from ideal. Less energy is released compared with complete combustion, and toxic carbon monoxide gas can be produced. Earlier we asked whether it matters how an alkane burns, and the answer is yes. When combustion is complete, we release the maximum amount of energy and produce carbon dioxide and water. But when oxygen is limited, incomplete combustion occurs. Less energy is released and dangerous products such as carbon monoxide can be formed. But carbon monoxide is not the only consequence of burning fuels. In the next video, we'll explore the pollutants produced during combustion, the problems they cause, and how we can reduce their impact. As always, the full topic playlist is on your screen now, and if you found this helpful, please consider subscribing for ongoing support with A-level chemistry.